Okay. All right, everyone. Welcome to class. Welcome to a new section. Okay, so in this section, our subject of discussion is going to be um, absolute convergence. So 11.6, absolute convergence. All right, so the ratio test. And then we conclude this session by studying the root test. Okay, so we started following the Stewart book closely from day one of the class. So this is 11.6. All right. So let's start with definition. Let's start with absolute convergence. Absolute convergence. Okay, so we are actually getting a lot of tools in our toolbox. We already have the test for divergence. We already have integral tests. We have the comparison tests, as well as the limit comparison test. Okay, so we saw all of those in the previous sections. So in this section, our focus is to get more tools by looking at absolute convergence, ratio test, and root test. Again, all of these don't actually give us the exact sum of the series. It only helps us to determine if the series converges or diverges, okay? So they are tools that get us informed about the behavior of the series. So definition. Okay, so a series, when is a series said to be absolutely convergent? Okay, so a series is absolutely convergent. Okay, so let me underline this word. If the series of its absolute value, okay? So let me put a parenthesis, say series of its absolute value is convergent. All right, so a series is absolutely convergent if the series of its absolute value, just from the name absolute convergence, okay? Now let me note if a series has all positive terms, okay, so if the terms of this series are all positive, now what do we mean by that, guys? So that means an is bigger than or equal to 0. If a series has all positive terms, then what would the series of the absolute value be? It's just going to be the same thing. Okay, think about this. You have absolute value of 5. 5 is a positive number, so nothing changes. So this is just 5. Okay, so in this case now, our an is already positive. So if you take the absolute value of the positive guy, it's still the same thing. Okay, so it's something to, to remember. So that means this guy, and so absolute convergence is the same as the usual convergence. Okay, okay. Now this happens when the terms of the series are all positive. Okay, so the absolute convergence is just the same as convergence. All right. Now let's look at an example, example 1. Now I really need to investigate. So let's say investigate the convergence or divergence of this given series. And from 1 infinity, this is a negative 1 to the power of n, all divided by n cubed. All right, we want to investigate this convergence or divergence of this series. So what do we do? Now, because we're talking about absolute convergence, I really need to think about the series of this absolute value. So what does that mean? I got to think about something like this, -1 to the power of n divided by n cubed. My indexing, I'm going from 1 to infinity. Now, keep in mind that you have, now this -1 to the power of n tells me that I have alternating signs. Now, remember that if you have absolute value of -3, this just gives you 3, right? Or if we have -5, this gives us 5, right? So now think about this, guys. -1 to the power of n divided by n cubed. In terms of the absolute value, what does the absolute value do? It's going to get rid of the negative sign. So that way you just have 1 over n cubed. Now you might have a question like, okay, why don't I have 1 to the power of n? Okay, if you have 1 to the power of 1 million, it's still 1. So that's why I just, think less about that n. Make sense? So that means this guy is exactly going to be n from 1 to infinity, 1 over n cubed. Okay, so let's think about this guy. What kind of series is this? I can just use the P series test, right? This guy converges. Now, what am I using the P series test? The P test, my P is 3. And what is the P test? As long as my P is greater than 1, that series converges. Okay, remember that? Okay, so what is going to be my conclusion? My conclusion is just going to be that this guy, the original series, converges since this guy okay, so I'm missing a -1 to the power of n, since this guy converges. Now, can you see that in this case now, the convergence of the original series is dependent on the convergence of the series of its absolute value? Okay, so this idea of the absolute convergence comes in handy when you have a series of alternating terms. Okay, so when you have a series with alternating signs, so you have a negative, positive. So it could even be -1 to the power of n plus 1 or n minus 2, whatever it is. So when there's a negative there, this caters for it. Okay, so but when you start having like let's say 1 to the power of n, or just 1 over n cubed, so you don't have to think about absolute convergence. Why? Because this is what I mean. Suppose the original thing we're handling is this. Now, so this way I don't have to think about, so let me say, don't have to think, so that you don't think it's the same question. Let me just change this to 5. So don't have to think about absolute convergence. Since what, guys? My an, which is 1 over n to the 5th, is positive. Let me start this guy from 1, yeah. Okay, so, and that's exactly the notes we have right on top here, okay? Okay, so let's make some progress. Now, another example, example 2. Now we're given this series, -1 to the power of n, all divided by the 5th root of n squared. Okay, so now this guy, can you see the alternating term, -1 to the power of n? So what do I do? So I gotta think about the series of its absolute value. So that means I'm gonna put an absolute value here, divided by the 5th root of n squared. Okay, so now let's come here and say, okay, what is this guy? Of course, the absolute value gets rid of the negative on top. 1 to the power of n is just 1. So you have a 1 on top. the fifth root of n squared. I can write that guy as n to the power of 2 over 5, right? So this is going to be series as n goes from 1 to infinity, 1 over n to the power of 2 over 5. So now here we are, right? So over here now, what kind of thing is this guy? I can still use the p-test, right? This guy is divergent. Why does it diverge? Because p, which is 2 over 5, is less than 1. And that's still the p-test, right? So if this guy diverges, what does it tell us, guys? It means the original guy is divergent. It means the original series is divergent. Okay, so this is when you use the absolute convergence. Now, by the virtue of absolute convergence, we got to think about the convergence of its absolute value. Okay, now there are sometimes you have it when the original series may converge, but the series of its absolute value may diverge. We're going to have a situation like that. We have a special name for that, and that is called the conditional convergence. Okay, that is what we call the conditional convergence. So I'm going to write something about that. Okay, so now let's see. So let me write in red. However, if Bn is 1 over n, this guy. Now, what is going to be B sub n plus 1? That means wherever you have n, replace it by n plus 1. Now, this guy I have in red, I want to show you guys that when the series of absolute value of when the series of absolute value is divergent, it does not necessarily mean that the original series is divergent. The original series may converge and the series of absolute value diverges. But if the series of its absolute value is convergent, then the original series will converge. Okay, I hope that makes sense. All right, let's go. So this is going to be 1 over n plus 1 to the power of 2 over 2 over 5. Okay, so let's see. So by comparison test, what can we see? My b sub n plus 1, which is the same thing as this guy, is less than 1 over this guy, which is my b sub n. Okay, so what can I see? The limit okay, as n. In this case now, I want to treat this as, if you guys remember, I think I can show you from here, the limit comparison tests. Okay, so let me show you a quick one. Let's go back to the limit comparison tests. Okay, so this is alternating. So let's go to 11 points. I think that's 11.4. Oh yes, perfect. So in 11.4, let's see this guy. Okay, so now this is, I'm just going back, guys. I'm going back to what we've seen before. And this is 11.4 where we talked about the limit comparison tests and the comparison test itself. Now, at the level of limit comparison tests, we are actually finding the limit of a quotient, the limit of an over bn. All right. So if you find that limit, sometimes you get, now in this case now, this is my bn is n squared over n cubed, which is 1 over n. Of course, the series of bn is harmonic. So I have to keep that in mind. So when I solve this guy, I have a 1. Now, that's because of the statements. This is just reminding you guys. Okay, so this is particularly reminding you that when this limit gives you a finite number, what do you expect? It either diverges or converges. Okay? Makes sense? Let me go back to where we're at right now. So this may not be the best example to throw at you, but let me go this way. Let me go this other way around. Let me take off this guy. Sorry about that. Let me go this way around. So let me say that, okay, sometimes it's better to write it this way. Sometimes, yes, the series, this guy, may converge. Okay, so let's go this other way. So sometimes the series of its absolute value may diverge. And the series without the absolute value may converge. This situation is possible. This situation is very possible. Okay, so now let's see what situation that is. Definition. So this leads us to the definition below. Okay, I think it's better to come from this angle rather than from what I was trying to prove the other time. Okay, so this leads us to the definition below. Okay, so and that's conditional convergence. Okay, so a series is conditionally convergent if it is convergent. A series is conditionally convergent if it is convergent. So let me underline conditionally convergent and not absolutely convergent. Now, there's a theorem, guys. There's a powerful theorem which I want to state right now, which says that if a series is, okay, let me write the series. If a series, this guy, is absolutely convergent, if a series is absolutely convergent, then it is convergent. Now, I'm going to write this in a way you guys are going to understand very well. Now, if I want to summarize this, okay, so let me just write a summary here. The summary is that absolute convergence implies convergence. Now, I gotta put the caveat. If the terms of the series are not, if this guy does not hold, what do I do? So if the terms, let me write it in word. If the terms of the series are not all positive, that is, have alternating sign, yeah, okay. So I'm trying to, put it together in a layman's language. So if the terms of the series are not all positive, that is, they have alternating sign, what does it mean? When you check for absolute convergence, that implies convergence. However, convergence does not imply absolute convergence. Okay, whenever a series converges absolutely, that means the series is convergent. But when a series converge, it does not mean that the series converge absolutely. Okay, keep that in mind, everyone. Keep that in mind. And that is the subject of conditional convergence. Okay, so in summary, what is conditional convergence? Let me call this 1, let me call this 2, let's call this 3. Conditional convergence is when this guy converges and this guy does not converge. Okay, think about that, guys. Think about this summary. Let me give you guys a minute. Think about this summary. Okay. Have you thought about that, guys? Okay, so now let me show you an example. Okay, so this example is going to cover up for whatever I was trying to prove the other time. So example 3, I guess. So we want to investigate the convergence. In this case now, we want to investigate the convergence or divergence of this guy. Infinity, -1 to the power of n over 5n plus 1. Okay, so we want to investigate, yeah, convergence. Now, if we talk about convergence, this could now mean absolute or conditional convergence. Okay, so what do I do? Now, keep in mind that if a series converges absolutely, that means the series is convergent. So I need to just first start by going this way, -1 to the power of n divided by this guy. Okay. Now, if you do this, you would have this guy. Now, but if you have this, the problem is this. From what we have seen so far, n from 0 to infinity, n from 0 to infinity, right? Now, from what we have seen so far, how do we check the convergence of this guy? This guy. Which of the previous tests do we use? Can we go ahead and use the test for divergence? Not quite. Because if you use the test for divergence here, the limit of this an in this case is going to be 0. If you have 0, it doesn't really tell you anything. That's inconclusive with respect to that test. But I can actually do the limit comparison test. Okay, I can actually do the limit comparison test. So I'm going to say, let me choose a red pen. So let an be equal to 1 over n. And let us call our bn 1 over 5n plus 1. Now to show, now when you put in the absolute value, right, you don't always have a p series in the end. Okay, so don't get that wrong, guys. You get something else, then you think about the previous test we have learned so far, which of them will help you going forward. Okay, so we are moving to a bit into the material where we have more technical details. Okay, and you have to rely on the previous tools you have in your toolbox. So let this happen. Okay, so what is using the limit comparison test? Now, what do I need to do? I need to check this guy, an over bn, right? And this is like you have limit as n goes large, 1 over n divided by, you got a 1 over 5n plus 1 on the bottom. Okay, so this guy is going to be, now this guy is going to change flip, right? I'm going to have a 5n plus 1 divided by n. How do you find the limit of this type of thing? You divide the top and bottom by the highest power of n over 1. Okay, so this is just by saying that you do have a 5n divided by n plus 1 over n divided by 1 over n. So this exactly is going to be limit as n goes large. You got a 5 here plus 1 over n, right? What is this limit, guys? 5. What kind of number is 5? 5 is greater than 0. Okay, so now does this converge or diverge by the limit comparison test? What do I have to think about? I will go back to my an. Tell me about the series of an. This is harmonic. What happens with harmonic series? Diverges. So that means that so n from 0 to infinity, 1 over 5n plus 1 diverges by the limits comparison test. Okay, interesting, guys. Interesting. Now remember again, how does it diverge? You have a positive number 5. You go back to the series of an. Okay, so let me write it here. So since this guy diverges. Now, but keep in mind that, guys, this is this, what we've done so far is the series of the absolute value. It diverges. Does it mean that the original series diverges? The answer is no, not quite. Okay, not quite. So now, let us investigate this guy. I have put the absolute value. It looks like it's not giving me what I want. It diverges. So let me see if this guy diverges. Okay, I'm going to give you guys a summary when we finish solving this. Now, if you want to investigate this guy for convergence, what can you use? What test can you use? This guy has alternating sign. Do you guys remember the AST, the alternating series test? Okay, so use alternating series test. AST. Now, in this AST, keep in mind that there are a few things we need to check. There are 2 conditions primarily that must be satisfied. Our Bn must be decreasing, right? So let me come here and say hypothesis. Hypothesis of the alternating series test. And the second thing is that the limit as n goes large of the Bn has to be 0. Now, can I say at this point, guys, that now at this 11.6, you really need to be familiar with everything we've done from 11.2 when we started series to 11.5, because you need those tools from your toolbox to really figure out what you do exactly. Okay, so I need to show this guy. In this case, of course, my Bn is negative 1 to the power of n over 5n plus 1. No, there's no negative guy. It's just going to be 1. Because my Bn is that part that doesn't factor out, that doesn't factor in the alternating signs. So is this guy decreasing? So 1 is, let me give a space. 1 here. is Bn, which is 1 over 5n plus 1, decreasing? Okay, so let me put this guy here. What do I need to do? So I'll say consider, remember the first derivative test, right? F of x equals 1 over 5x plus 1. What is f prime of x? F prime of x, first derivative, is going to be 5x plus 1 multiplied by 0 minus 5x plus 1. So I think it's advisable not to skip step, guys, so that I can make sure that I don't lose anybody. So let me write here 1 factorial divided by this guy on the bottom squared. I miss a parenthesis here, okay? So 1 factorial is 0, so that means this guy goes to 0. F prime of x is going to be a negative 5 divided by 5x plus 1 squared. Talk to me, guys. This guy is less than 0. So thus Bn is decreasing. The second part is that is the limit as n goes large of Bn equals 0. If these two conditions are satisfied, guys, remember the alternating series test helps you to show convergence, okay? Is this guy true? Let's see. Limit as n goes large of 1 divided by 5n plus 1 is exactly 0. Awesome. So this guy, n from 0 to infinity, negative 1n divided by 5n plus 1 is convergent, right? Converges by the alternating series test. Okay, so what's our conclusion, guys? What's our conclusion? Now, what do we know? This guy, the series of this guy diverges, but the series of this guy converges. Interesting. What is our conclusion? Conclusion is that the original series is what, guys? Does it diverge? No, it is conditionally convergent. Yes. Amazing. Okay, so absolute convergence is stronger than conditional convergence. All right. So there are times when you check the series of the absolute value and it diverges, that doesn't mean that the series without the absolute value diverges. You only have to check. Okay. If you check and it still diverge, then the whole thing diverges. Make sense, guys? Okay, so let's talk through this example again. So here we wanted to investigate the convergence of this guy, whether it is conditional convergence or absolute convergence. So the easiest part to start from is to start from the series of the absolute value. If it is absolutely convergent, then I need not to worry. The original series is convergent. But now in this case now, I had to do the series of the absolute value using the limit comparison test. The series of absolute value diverged. Now, since it diverged, that doesn't mean that the original series diverges. Okay, I only need to check if it is true that it diverged or not. So you go back to your original series, which is the question itself. Now you think about it, what test can I use to investigate it? Okay, you look at the form, it's an alternating series. Use the alternating series test. The alternating series test has two hypotheses. The first one is that your Bn has to be decreasing. And the second part is that your limit of Bn has to be equal to 0. Okay. So, and in that case, you check. And that's what we'll try to do here. Is this guy decreasing? We use the first derivative test. It was actually decreasing. We came over here and said, oh, okay, it's the limit of bn equals 0. And truthfully speaking, it equals 0. So by the alternating series test, we conclude that the original series converges. Okay. Now, but we need a bigger conclusion. Now that takes us back to what we're studying. Now, since the series of absolutes value diverge here, but this guy converge, that means that the original series is not just convergent, but conditionally convergent. Okay, I hope this makes sense, guys. All right. Now let's do another interesting example. Example 4. Determine whether the series is absolutely convergent. So solution. Now, when you see something like this, especially when you have this trigonometric quantity involved, so you always have to think in terms of doing something with the idea of sandwich theorem. Okay, why? Because of course I know that my sign is between 0 and 1, right? Now I'm going to make some kind of construction. Now, but you see this guy on the bottom is 2 to the power of n. Now, 2 to the power of n, when n is from 1 to infinity, is always positive. So think about dividing the whole of this guy by this. If you put it here, 0 divided by something, which is 0 divided by a positive quantity is 0. So I care less about that guy. Okay, that's the first stage of the construction. But what do we need to check? Absolute convergence. Take note of the word. So that means I need an absolute value on this guy. So it's okay if I put an absolute value here. It doesn't change anything. Okay, so what do we know? Now, keep in mind that if the question is about the limit of the guy in the middle, okay, the limit is just going to be 0. But that's not our interest, guys, okay? So what do we know? This guy on the extreme right, if this guy converges, that means this guy is convergent. So remember comparison tests, okay? This guy is a convergent geometric series with my common ratio 1/2, which is less than 1. Okay, so what's going to be my conclusion? This guy converges. My conclusion is going to be that this guy to the power of n converges. Now, why? By what test, guys? By comparison tests. Now, it converges, but keep in mind that, but it has the absolute value. What does it mean? Interesting. It's absolutely convergent. Okay. Now, when you understand these principles, I mean, it's very interesting to handle. When you have this kind of trigonometric quantity involved, you rely on, okay, sine or cosine is between what and what, then you construct. So I try to construct, I made the first stage of construction, second stage. Now, what is a series of this guy on the extreme right? What kind of series is that? It's geometric in nature, okay? So in fact, if I even want to make it better, I can just write something like 1/2 to the power of n. Because they are the same, okay? So you don't worry about that. This guy is the same thing as this guy. It's a convergent geometric series. Your common ratio is half, which is less than 1, and then you have your conclusion. Okay, so let me make a statement. There are a pair of tests that we can use to determine if a series is absolutely convergent. And those are the new tests I want to introduce now, okay? Okay, so let me just say below are a pair of tests, okay? Below are a pair of tests that we can use to determine if a series is absolutely convergent. Now, these new tests we want to talk about, we've not actually studied them, okay? So there are additional tools that you can use apart from the ones that you've known, okay? Below are probably, I see below are new pairs of tests, yes, that we can use. Okay, so let's go. The ratio test. I've seen that a lot of students love this ratio test because they consider it's very easy to use. So what is the statement? Let this guy be any series. Number one, if the limit as n goes large of this guy equals L. If you check the limits, well, if L is greater than 1, then this guy is absolutely convergent. What is the second statement of the theorem? Now, what we are actually measuring is this guy. We do the same thing. If it gives me a limit that is bigger than 1, or perhaps if it gives me a limit, if it just gives me infinity, then now think about it. When you have infinity, what do you expect, guys? You have some kind of divergence, right? It's divergent. There's nothing like conditionally divergent or conditionally, absolutely divergent. You just say divergent, okay? So we don't use those terms such as absolute divergence, we don't, or conditionally divergent, we don't, okay? So if limit as n goes, now, but there are times when some tests would not work, you know, when we say they are inconclusive. If this guy gives me 1, if he gives me 1, then the ratio test is inconclusive. So that means you have to think about another test to use. That means the ratio test is not the way to go. Okay, so that is no conclusion can be drawn about the convergence or the divergence of this guy. Okay. All right. Now let's do some examples to help our understanding of how ratio test works. Okay. Example. I give you the series n factorial. Okay, so we have done something with n factorial before. Okay. Now, the first thing you need to identify is your an. Your nth term, this guy is -3 to the power of n divided by n factorial. Then you move on from there. What is going to be an? Now, take notice, guys. What we are really measuring, or what we are trying to find the limit is this quantity, this guy. So I know an, so I need to know what this guy is. Okay. what is going to be a sub n plus 1? That means wherever you have n, plug in n plus 1. So that means you have a negative 3 to the power of n plus 1 equals n plus 1 factorial. Now, but think about this. Can I simplify the guy on the top? Yes. So you can write this guy as negative 3 to the power of n times negative 3 to the power of 1, right? All divided by, now remember when we talked about factorial, this is n plus 1 factorial. So if I want to split this guy, I start from n plus 1. The next guy becomes n plus 1 minus 1, and that's just n. I can halt it at that point. Okay. Why? Because I taught you guys before that if you have 5 factorial, you start from the largest 5. You decrease by 1, 4. You decrease by 1, 3. You decrease by 1, 2, up until 1, right? But sometimes you don't want to get to 1. So what can you do? You can halt it at a point. If I need to halt it at 4, I'm going to put a 4 factorial here. Make sense? That's exactly what I did. So now let's now get down to the limits. Limit as n goes large of that quantity, okay? Limit as n goes large. Now, what is my a sub n plus 1? That is negative 3 to the power of n times. Now, I'm using the simplified form because when you do ratio test, actually, some things cancels out. Now, you have a division sign here. So this is divided by an. Now, but an is a fraction. So if I plug it in, change flip, n factorial divided by, so at this point, let me use the red for an. Yes. Cool. This guy takes off this guy, right? This guy takes off this guy. So what are you left with? You're left with limit as n goes large, negative 3 to the power of 1, right? Divided by n plus 1. But think about it, guys. Absolute value of negative 3 to the power of 1 is negative 3. But what does the absolute value do? It's going to take rid of the negative sign. Talk to me. What is this limit? 0. So now my L is 0. What kind of number is 0? Less than 1. So what does it mean? It means what, guys? It means the series is absolutely convergent. Okay. Okay. I remember that absolute convergence means convergence. So I can just write convergence. Okay. If you want, you can write absolutely convergent. Okay. So interesting. Let's look at another example. So in this example, you have 2 to the power of n, n plus 1, n plus 2. All right, so this is, I'm counting from, let me see, I'm going from n from 1 to infinity. All right, so what else do I do now? Okay, so let me see, just making sure I have the correct problem. Okay, so this is 2 to the power of n. Okay, yeah, divided by, this is n plus 1, yes, n plus 2. Now, okay, we really want to use the ratio test. So what is my an? 2 to the power of n divided by n plus 1. Now, while working on the ratio test, you have to ensure that your algebra is good, okay? This is n plus 1. You have to avoid errors doing the little algebra thing. Whenever you have n, plug in n plus 1. So that means I have n plus 1 plus 1. and then I have a n plus 2, n plus 1 plus 2. An plus 1, simplify this guy. This is 2 to the power of n times 2 divided by, you got a n plus 2 and then n plus 3. So now I'm going to get down to the limit itself. Limit as n goes large, put your absolute value an plus 1 or an. Is the limit as n goes large. It's 2 to the power of n times 2, all divided by n plus 2, n plus 3. Multiply by, now when you plug in your an, let me write that again in red, change flip, n plus 1, n plus 2, all divided by what? 2 to the power of n. So what can we see? This guy cancels this guy. This guy takes off this guy. I'm actually going to be left with the limit as n goes large. I'm going to have a, okay, so let me not skip step. Now this is 2. 2 is a constant, you can pull it up front. N plus 1 over n plus 3. Now, but this quantity are positive, so I can take off the absolute value. But this limit equals 1. So that means you have 2 times 1, which is 2 times 1, which is just 2. Now, that means my L is 2. What kind of number is 2 greater than 1? What's the conclusion, guys? Diverges, okay? So what diverges actually? The series is divergent. Okay? And keep in mind that you can just come here and write by. Okay. Now be careful of using abbreviation in ratio test, because if you write RT, we still have root test. So that's still RT. So it can be confusing. Okay. All right. So let's move on to another test, the root test. Now let's write a statement of the root test. Let this guy be any given series. Okay. The same thing if the limit, but in this case, we have a little twist. We have the nth root of the absolute value. That's the twist. If this guy gives me a limit that is less than 1, then this guy is absolutely convergent. ABS convergent means absolute convergence. If this guy, again, nth root of that guy, if he gives me a limit that is greater than 1, or the same thing, or infinity, then what happens is divergent. And the last statement is that if that same limit equals 1, the root test is inconclusive. And I explain what the inconclusive means. Now, let me give you guys a hint. This may come in handy at some point. It is convenient to actually apply the root test, when nth power occurs. Now let me write number one hint. Number two hint is to tell you guys the limit as n goes large of the nth root of n is 1. The limit as n goes large of the nth root of n is 1. Okay. Let's consider some very nice examples. Example. So that's n to the power of n divided by 3. Then you have 1 plus 3 to the power of n. Okay, so what do we know? Let's go back to our an. N to the power of n divided by 3 to the power of 1 plus 3n. Right? Now, for the root test, what are we doing? Essentially, we are checking the nth root of this guy. Okay, so can we do that together? Now, keep in mind that you don't need the absolute value sign when you're sure that this guy is positive. So, of course, I know this guy is positive, so I will care less about the absolute value in this case. So, limit as n goes large, nth root of n to the power of n divided by 3 to the power of 1 plus 3n. Interesting. This is limit as n goes large, nth root of n. To make sure I write it clearly. Divided by the nth roots. Of course, this is just some kind of simple indices. Okay, so what do we see? This guy is actually going to be the limit as n goes large. This is going to be n. The guy on the bottom, I'm going to have something like this guy, 3 to the power of 1 over n plus 3. Now think about this. I don't need to stress myself. As n goes large, this guy will go to 0, right? So you have 3 to the power of 3 on the bottom, but on the top you have infinity. So that's going to be undefined. So conclusion diverges a series by root test. Root test. Okay, I hope it makes sense. Now let's look at one last example here. We have a 2n plus 3. Then you have a 3n plus 2 to the power. Remember, the hint was that you use this guy when the nth power occurs. Okay. If it doesn't occur, then you run into some trouble of trying to understand what to do and everything. Okay. Now I will not bother about the absolute value here because I'm sure that all of these guys are, this guy an is positive. So I move to the next phase, the limit of the nth root of n, right? Nth root of an, I mean, this is 2n plus 3 over 3n plus 2n. Limit as n goes large. Keep in mind that you have 2n plus 3 over 3n plus 2. You got an n here. But this is like nth root of something. So you have 1 over n. This guy takes off this guy. Amazing. Limit as n goes large. 2n plus 3 divided by 3n plus 2. Talk to me, guys. This limit is just 2/3. My L is 2 over 3. What kind of number is 2 over 3? Is it less than 1 or bigger than 1? It is less than 1. So what's going to be our conclusion? So thus, the series is absolutely convergent by the root test. And so it converges. So it is convergent. Okay, so let me give you guys some things to try. The first one I'd like you guys to try. And I'm going to tell you what the answers are so that when you try them, it can be consistent with what you have. Use ratio test. The conclusion here is that it is inconclusive. And then the second one, let me give you one also from roots test. In fact, as a matter of fact, guys, I can even make this number 2 interesting. I can say use ratio test and root test. Conclusion is that it converges. Okay. Okay, so yeah, you got to use it should also converge in both cases actually. But looking at this, I did it with the roots test. So, but looking at this, it should also converge with the ratio test. Yes. All right, guys. I hope all of this makes sense. Okay. See you in the next session. Bye-bye.